In this video, we're going to go step by step through all the solutions to the problems on the Algebra and Trig assessment test that you have taken. This will show all the background Algebra and Trig that you need to solve the problems, and also show Algebra and Trig procedures and techniques that we'll be using throughout this course and Calculus 2. So here we have problem 1 where we're solving this equation for x. The first step is to distribute the coefficients across all of the binomials, and so let's do that first. So first let's notice that when we do the distribution of the coefficient across this binomial, that we're distributing the minus sign. So let's now, in our next step, collect the terms on the like terms on the left side, and that gets us to this point, and then we're going to isolate the x on the left side and move the constants to the right side, which gets us to this point. So this problem is such that when we move the 7x over, we already have x isolated, and when we move the 5 over, we have the solution x equals 65. So let's move on to problem 2. So in problem 2, we're solving for x. We want to move this z term over to the right side, and then the only thing that remains to be done is to divide through by this coefficient of x10, so that we have x isolated on the left, and then we have the solution for x, which is in terms of z. So let's move on to problem 3. So we are simplifying this expression. Notice that we have an expression within an expression, so let's distribute the minus sign here and write what we get in the next step. And now that we've done that, to get this, notice that there's a minus sign in front of the 1, but a plus sign in front of the x, because it's a minus times a minus here. Now we're going to distribute the minus 2x across everything inside the brackets. So let's notice that we have these three like terms in x squared, and we're going to combine those terms in the next step. Excuse me, I had this term right here copied incorrectly as 4x squared, so it's corrected here, which corrects this term. So now let's combine like terms. So we've done that, and now let's factor out the common factor, which is x. It's actually better to factor out a minus x, because these first two terms and the leading term have a negative in them, and so now we have an answer in the simplest form with the minus x factored out. It's certainly okay to leave the expression like this, in the sense that it's not wrong, but it is in a little bit simpler form if we factor out the minus x. You could have factored out an x, and it would have been correct to do that also. So let's move on to problem 4. Okay, so in this problem we're going to combine these two coefficients into one coefficient, first noticing that this 2 goes into this 12. And so if we combine the coefficients together, we have 11 over 54. So in doing the next part of this simplification, where we are multiplying the x times the x to the fourth and the y to the fourth times y cubed, so we're multiplying this times this as well as the y to the fourth times this, we need to use the rule for multiplying expressions with the same base and a different exponent, and that is that we add the exponents. And so if we do that for the x, we've got first power on this term and a fourth power on this term, so that gives us x to the fifth, and we've got a y to the fourth here, and a y cubed here, so when we combine the exponents, adding them, we get y to the 7th. And so there we have our simplified result. So let's move on now to problem 5. So in doing this problem, we are, for the most part, going to use this exponent rule because we have variables with the same base and different exponents across the numerator and the denominator. So let's circle the pairs. Okay, so we have the x in the numerator and denominator identified, the y in the numerator and denominator identified, and the z. And so using this rule right here, let's see what we get. Right, so combining the x's, we get exponent 8 in the numerator minus 6 in the denominator, giving us x squared. On the y's, we have a 4 exponent on y in the numerator, 1 exponent of y on the denominator, giving us y cubed. And for the z, we have power 8 in the numerator, 5 in the denominator, giving us y cubed, or z cubed. And so there's the result written a little bit nicer with everything in the same color, or a little bit easier to read with everything in the same color. So let's move on to problem number 6, where we are using these two rules as well as rules for exponents with radicals. So let's first note that if we have an nth root of x to the m power, that can be rewritten as x to the m over n. So the numerator is the power and the denominator is the root. Let's also note that if we have x to the minus n, a negative exponent means move that exponent to the denominator, and we also can do that in reverse. If it's negative in the denominator, it is positive in the numerator. So let's apply that to these 6a, b, and c. So the instructions in this problem are not to have any denominators, so we would rewrite this one in its negative exponent form as 2x to the minus 3, moving the 3 up as a negative exponent. In 6b, we're using this rule for roots and powers to rewrite this as 12. The power on the x is 3, and the root is 2. So the power goes in the numerator, 3, and the root, square root, goes in the denominator, 2. So this 6b is 12x to the 3 halves. For 6c, we want to move the x up to the numerator as x to the minus 1. And so there we have that one done just in one step. And then for 6d, we are using this rule, so the root in the denominator, the power in the numerator. And so that cube root of x is x to the 1/3, and then we're raising that to the 6th power. Now to continue on this problem, we have to use this rule for exponents right here. So we have a function or an expression to a power raised to a power. We multiply those two exponents together. Let's do a quick example to illustrate. So if we have x cubed squared, that's the same as x cubed times x cubed. We add the exponents to get x to the 6th, but a much faster way would have been just to multiply those two exponents together to get 6. So continuing in the denominator, we have minus 5. We multiply the exponents together to get multiplying the 1/3 times the 6 to get x squared. And then the objective is not to have denominators, so we rewrite finally like this. So we move that x squared in the denominator up to the numerator as x to the minus 2. So in this next problem, we're combining a non-fraction with a fraction, and what we need to do is get a common denominator. This 3 does not have a denominator, but if we write it this way, we see that its denominator is 1. Now in getting a common denominator, we can get a common denominator. So let's first note that we can get a common denominator as by just taking the product of all the denominators involved. So in this case, that's just 1 times y plus 6, which is just the y plus 6. Now there is also a least common denominator, you recall. That's a little bit more complex to define in words. I'll do it and then we'll talk it through how it applies to this problem. So the least common denominator in words is we start with the product of all denominators. But then we have to have each distinct factor raised only to the highest power it occurs in any one denominator. So I want to illustrate that with a more complex set of denominators on the next blackboard. So what I've done first is just multiplied all these different denominators together, and that is a common denominator. But that is much more complicated than the least common denominator. For the least common denominator, we would take all the distinct factors, which are x, y, z, and w, and raise them only to the highest power they occur in any one denominator. So the x occurs to its highest power here, the z to its highest power here, the y to its highest power here, and the w to its highest power here. And so here is the least common denominator. So you can see that the least common denominator here has the factors to a lower power and is going to give you a much more simple expression than if you use just the common denominator. So going back to where we were with this problem, in a lot of cases, the common denominator and the least common denominator are the same. It's just calculated as the product of all the denominators, which is the case here. So the LCD is the common denominator. So let's find let's combine these two fractions with that common denominator. So this fraction right here did not have y plus 6 as a denominator. We're wanting to make it so that it now does. So we're going to have to take that 3 and multiply it by what wasn't there in the denominator before, y plus 6, whereas with the other numerator, the 2y plus 18, it already had the denominator of y plus 6, and so we don't have to make any change to that. Let's also notice this, that if we were to take this part of the fraction right here that we're building and cancel out this y plus 6 and this y plus 6, we're back to the 3. So we just built it up in that part. So now we're going to distribute in the numerator to get 3y plus 18, and we're going to distribute the minus sign here to get minus 2y minus 18, and that's of course over this denominator of y plus 6, combining like terms, and noting that the 18 cancels, we just get y over y plus 6. Okay, so let's move on to the next problem where we're combining fractions and again getting a common denominator. In this problem we're multiplying fractions. When we multiply fractions, here's a model. So we've got the first fraction 1/3 is of the form a over b, and the second fraction, x minus 6 over 3, is of the form c over d. We're multiplying fractions. We don't need common denominators. We just multiply the numerators and multiply the denominators. So doing that, we get x minus 6 in the numerator and 9 in the denominator. 9 halves in the denominator. Now, we now have a fraction of the form a over bc. The bc part is the 9 halves. We want to invert and multiply. So we're going to take this bc, and instead of dividing by that, we're going to multiply by c over b to get ac over b. The c is 2, and so bring that 2 up into the numerator, and now we need to distribute the 2 across the x minus 6 to get 2x minus 12 over 9 as our simplest form of this fraction. Okay, so this problem is put in here because we want to avoid making a mistake if what we have is a problem of this type, a squared minus b squared. If instead we had had a quantity a plus b squared on the radical, then we have something squared under the radical and it would come out as a plus b. Whereas in this case, we can rewrite the expression under the radical like this, but it's not something squared under the radical, and so this problem does not simplify at all. There's no value in writing it this way, and so NA is the answer because there's not any way to simplify it. In this next grouping of problems in 8, we are solving equations. And so in this first equation that we're trying to solve for x, we need to remove the radical on the left side, so we're going to square both sides, and that will remove the radical on the left and square the right hand side to give us 36. When we are solving quadratic equations, we need to put them in the form ax squared plus bx plus c equals 0, and then determine whether we can factor or, and then so we've written our quadratic into the form ax squared plus bx plus c equals 0, and we're going to first see if we can factor it. So we notice that the 56 can be written as 7 times 8, and that 7 plus 8 equals 15, so that tells us that it does factor. And it factors like this: x plus 7, x plus 8 equals 0, 7 times 8 is 56, and when we combine the two middle terms, that gives us the 15x. So we have an equation of the form a times b equals 0. That means the factor a equals 0, we set it equal to 0, and the factor b equals 0, we set it equal to 0. And so in setting those two factors equal to 0, we get the two solutions: x equals minus 7 and x equals minus 8. So in this problem, we have to put it into the a squared plus or ax squared plus bx plus c form that quadratic equations need to be in, and then determine whether we can factor it or use the quadratic formula. There are no factors of 2 that when we add them together are going to give us the 4, so we have to use the quadratic formula. So we've got the quadratic formula written here, and when we apply that to this problem, the b is 4 and the c is 2, so we get z equals negative b plus or minus the square root of b squared minus 4. The a right here is 1, because that's the coefficient of the z squared. We said that c is 2, and that's divided by 2a, which is 2 times 1. So simplifying, we get minus 4 plus or minus the square root of 8 over 2. And I've written the square root of 8 as square root of 4 times 2, which allows us to take out the square root of 4, 2. So it's 2 times the square root of 2. I'm sorry, I made a mistake on this, so let me correct it. When we move this 2 over to the left side, that should be a minus 2 here, which puts a minus 2 here, which makes it under the radical 16 plus 8, square root of 24. We write that as square root of 4 times 6, bringing out the 2. So we are here, and now let's simplify that. So we rewrite square root of 24 as 2 times the square root of 6, and then that 2, when we divide it, it must divide both terms in the numerator, which it does. It cancels out the 2 in front of the square root of 6 and changes the minus 4 into a minus 2, giving us this as our most simplified answer. This answer right here is correct, it's just not in simplified form. So to solve this problem, we need to get rid of these denominators, and the way we clear the denominators on both sides is by multiplying both sides of the equation by the LCD. The LCD is the same as the common denominator in this case, just the product of the denominators, x minus 3 times x. So we're going to multiply both sides by x minus 3 times x. Now when we do this, it will clear out the denominators on the left side. So let's set it up to show how that happens. Okay, so first notice that when we multiply out the left side, we distribute the x times x minus 3 across both of these terms. And then in the first term on the left, we cancel the x minus 3. On the second term on the left, we cancel the x. So let's see where we stand on the next line. So we get to this equation here, which has no longer has any denominators. Also notice one more thing, that when we distributed the x times x minus 3, because of this minus sign here, we have this minus sign here. So let's work now with this equation right here, which is a quadratic equation, or will turn into a quadratic equation. So we want to put in the form ax squared plus bx plus c equals 0. So when we multiply out the left side, we get this expression here, and we're going to move everything over to the right hand side. So we're going to add the 7x over. Okay, fixing a mistake, this should have been a minus sign in front of the x here, which makes a minus sign right here. So now we're going to move everything over to the left hand side to get this equation. Okay, I've just noticed that I've got another error in copying the problem over. This denominator should have been x plus 3, so I'm going to start over on the next blackboard. So we're still going to multiply both sides by the LCD of the denominators on the left. That is x times x plus 3, and we're doing that on the left and the right. And so again, we cancel out term-wise. On the left side, the x plus 3's cancel here, the x's cancel here, and we can multiply out the left side to get this. And then we're going to bring everything over to the left hand side, so it's in the ax squared plus bx plus c equals 0 form that we need to solve a quadratic. And we notice that minus 21 has factors of 7 times minus 3, which when added give us the minus 4. So we're going to factor it that way. And when we do that and set those two factors, x plus 7 equal to 0 and x minus 3 equals 0, we get the two solutions, x equals minus 7 and x equals 3. Okay, so one more equation to solve on the next blackboard. Okay, and this next problem is not a quadratic, but we do not want to make the mistake of dividing through by n, which we could do, because when we divide through by variables or expressions containing variables, we lose roots. So if we divide it through by n, we would lose the solution n equals 0 that we'll see in a few moments. So we're going to bring the 72n over to the left side, and this is then a problem on the left side that we can factor. We can remove 2n from both factors, leaving us n squared minus 36. And now we have now we want to factor that further as 2n times n plus 6 times n minus 6 equals 0, which is an expression of the type a times b times c equals 0. So we set the three factors a, b, and c equal to 0, and after we do that, we see that we get three solutions: n equals minus 6, n equals 0, and n equals 6. And notice that this 0 factor here would have been lost had we divided through by n back on this first step. So in this problem, where we're finding the equation of the line passing through these 2 points, we are going to use the point slope formula. Y minus y1 equals m times x minus x1. We're first going to calculate the slope, which is going to be y2 minus, or we're going to use this y2 minus y1 over x2 minus x1 formula for slope, and so that's going to be 2 minus 1 over 8 minus 6, which is a slope of 1/2. And when we're using the point slope formula where we have 2 points, we can pick, we need to pick one of the points to use. It doesn't matter which one, but we're going to pick this one. We can't mix up the 2 points. We either have to pick point 1 or point 2. So we're picking point 1. So plugging in, we get y minus 1 is the slope 1/2 x minus 6, and distributing on the right side, we get y minus 1 equals 1/2 x minus 3, and solving for y equals 1/2 x minus 2. Okay, in factoring this problem, we notice that each term has a common factor of 3x, so that's our greatest common factor. We remove the 3x, which gives us minus x minus 5x plus 5x. This term is actually minus 3x cubed, so when we remove the 3x, we get minus x squared plus 5x plus 6, which factors further. It's a little easier to factor that second term if we remove a minus sign from all of those terms in the parentheses to get x squared minus 5x minus 6. Minus 6 has factors of minus 6 and positive 1, and so the final factorization of this is obtained by factoring the quadratic as x minus 6 times x plus 1. So we're supposed to expand this binomial squared. So first we're going to take minus 2x plus 1 squared, so that's the FOIL method. The first is minus 2x times minus 2x, which is 4x squared. The inner and the outer are the same, minus 2x and minus 2x, and then the last is 1 squared, which is 1. And if we combine terms and move the minus sign through, we get minus 4x squared plus 4x minus 1. Okay, in this group of problems we're simplifying and removing parentheses. So here we're distributing. The minus 1/4 times the 4 gives us a minus 1. That should be minus 1 over x out front. So minus 1 over x times 4 is minus 4 over x, and minus 1 over x times minus x is plus 1, but let's leave it in a form with the denominator, so it's plus x over x. So now we have a common denominator of x, and so that is minus 4 plus x over x, which is written a little bit more compactly as x minus 4 over x. Though it's fine to write it in this form, both are correct. So let's move on to 12b. X times x minus 3 squared. We square x minus 3. First, inner and outer are both minus 3x. We're using the FOIL method. Plus 9. Distribute the x across, combining terms, and we get x cubed minus 6x squared plus 9x. So we're distributing the 1/4 across these two terms. That gives us 2 over 4x plus 8 over 4x squared. The least common denominator, remember, is the product of each of the distinct factors, which are 4 and x, raised to the highest power. Each occurs in any one denominator. The 4 occurs only to the first. The x occurs to the second in the second factor. So with that least common denominator, the first numerator needs to be multiplied by x, because x multiplying the denominator by x would make it 4x squared, and the second numerator does not need to be multiplied by anything because it already has the denominator 4x squared. And then when we combine those terms, we get 2x plus 8 over 4x squared. There's a common factor of 2 in all of those terms, and so dividing everything through by 2 gives us x plus 4 over 2x squared as the simplest form of this combined expression, or simplified expression. In expanding this, to remove the parentheses, we just note that it's actually kind of just a notational problem. It's sine x times sine x that we are doing and removing the parentheses, and that is written as sine squared x, which is written this way. So what's boxed in is just the typical, more simple way of writing what we started with. So in this problem, we're removing, or we're rewriting, so there are no negative exponents. Remember the property that a to the minus m equals 1 over a to the m. And so here we've got 1 over 4x squared. The negative in the numerator becomes squared, or negative 2 in the numerator becomes squared in the denominator, and that gives us 1 over 16x squared. So in this problem, we are removing negative exponents. This term right here, a to the 0, is just 1, or this factor. The minus 4 and the minus 2 reduced to a 2 in the numerator. The b in the numerator and the b squared in the denominator, written without negative exponents, give us a b here, and the c with a negative 2 in the numerator becomes c squared in the denominator. And so there, this expression is written without negative exponents. Oh, excuse me. That was a c to the minus 3 in the numerator, so it becomes c to the third when we move it to the denominator, so it no longer has a negative exponent. So in doing these problems, we are in writing with no fractional exponents, we are writing a to the m over n as the nth root of a to the m, and we'll also be using this rule, a to the m raised to the n. We multiply those two exponents to get a to the mn. So here, when we multiply those two exponents, we get 27 to the 1/3 and x cubed to the 1/3. Actually, we're doing one step prior to that. So first we're using this rule that if we have the product raised to a power, it's each factor in the product raised to that power. So it is the factor 27 raised to the 1/3 power and the factor x cubed raised to the 1/3 power. And now we're going to use the a to the m to the n and combine exponents. So 27 to the 1/3 means cube root of 27, so that is 3. And x to the third to the 1/3, we multiply the exponents and get x to the first. And so our answer is much simpler than it looked originally. It's just 3x. So in this problem, it's easy to cancel the coefficients and get 4. When we combine the exponents, it is using a to the m over a to the n equals a to the m minus n. That gives us the exponent of 1 minus the exponent in the denominator, which is minus 1/2. So it is 4y to the 3/2. And if we write that without fractional exponents, using this property, we get 4 times the square root of y cubed, and we should note that that could also be written as 4 times the square root of y cubed. So the general property is this, that the nth root of a to the m is the same as the nth root of a raised to the m. Most typically we prefer this this because when we take the nth root first, we get a simpler expression or number, and then we raise it to the mth power. So either of these two answers is acceptable when we have a y variable. If we had numbers, most often we'd use this form. This is similar to a problem we encountered earlier. We do not have a quantity squared under the square root sign, under the 1/2 power, and so this expression is almost all simplified. However, we can factor 4 out of both of those terms under the radical, and Note that the square root of AB is the square root of A times the square root of B, and so this is the square root of 4 times the square root of x squared plus 16. Square root of 4 is, of course, 2, and the square root of x squared plus 16, there is nothing squared there and nothing more to remove, so we have to leave that as it is. And so here is our simplified result written in radical form. So here in this problem we get more practice with LCDs. We take all of the distinct factors, 3, 2, and x, and raise them to the highest power they occur in any denominator, which is 1, and so that is the LCD. The missing factor in this expression is the 2, so we multiply the 1 times 2. The missing factor in the 1 over 2x is the 3, so we multiply that by 3. And the missing factor in this final fraction is both the 3 and the 2, so we multiply that by 6. And so that gives us 2 plus 3 plus 6 over 6x, or 11 over 6x. So here we have an expression of the form a over bc. The bc is the denominator, the 2x squared over x minus 3. We're going to invert and multiply, so we get x times x minus 3 over 2x squared. And then we notice that the x in the numerator cancels with one of the x's here, and so in simplest form we have x minus 3 over 2x. And looking at this problem, we see that because there is going to be cancellation between the denominator and these two expressions, it's best to split this fraction, which has three things combined in the numerator, add and subtract in the numerator over denominator a plus b plus c over d, into three fractions. So let's split it into three fractions, and then we can see the cancellation clearly. Splitting into three fractions, we see that square root of x cancels here, and in this case here we're going to have to subtract exponents. And so here, when we combine the exponents, we get minus 7 square root of x, because it's a power of 1 in the numerator and a half in the denominator, which gives us, when we subtract exponents, exponent of 1/2, which is square root of x. So writing it out, we get x minus 7 square root of x, 7 square roots of x plus 3. So here we're doing long division in these next two problems. We actually do need to do long division in some problems in calculus. Notice that I've written an extra term in here in the numerator 0x, since we want a place for all powers of x. So the rule for long division is that we divide the highest power outside into the highest power inside, and so that gives us x squared, and then we multiply back x squared times x, x cubed, x squared times 2, 2x squared. We subtract. These will always cancel out. If we've done it correctly, we take 2x squared from 3x squared and get x squared. We bring down the next term. We divide, again, highest degree term outside and the highest degree term inside. That gives us an x. We multiply back and get x times x, x squared, x times 2, 2x. We subtract, again, 0 in this column, minus 2x, bring down, and we divide highest degree term outside into highest degree term inside. That gives us a minus 2. When we multiply back minus 2 times x, minus 2x, minus 2 times minus 2, minus 4, subtract 0 in column 1, minus 3, minus 4 is 1. And so this is our remainder over this denominator. And so writing this out, we have that the result is it goes in evenly x squared plus x minus 2 times, and it has a remainder of 1 divided by the divisor, which is x plus 2. So this long division problem has these 4 terms, the last one being a fraction. Okay, so in these final two problems, 17 and 18, we're doing trigonometry. In this first set, 17, we're just rewriting in terms of elementary functions. So secant is 1 over cosine, so secant cubed is 1 over cosine cubed of x. Cotangent is cosine over sine, and then we simplify as much as possible to give us 1 over cosine squared x sine x. Because the cosine here changes this power here to a 2. 17b, we are again reducing to elementary functions, tangent squared x times cosine x, elementary functions meaning writing in terms of sine and cosine. So tangent is sine over cosine, tangent squared is sine squared over cosine squared, multiplied by cosine x. The cosine in the numerator cancels with the cosine squared in the denominator to give us sine squared x over cosine x. And then in the third problem, the sine squared and the cosine squared do not change since they're already elementary functions. The secant here is 1 over cosine, so we bring it up to the numerator as cosine, and then just combine the last two factors. Cosine squared times cosine is cosine cubed. In the final problem, we should start with looking at the unit circle as a refresher, since most of these problems can be done easily if you know the unit circle. So in doing this problem, we actually only need the unit circle at the axes at these 4 points, and right at 0 degrees, at pi over 2, at pi, and at 3 pi over 2. And take note of the fact that when we have the coordinates of a point on the unit circle, the x value and the cosine are the same, and the y value and the sine are the same. So when we want the sine of the angle at 0 degrees, we're finding this y value, which is 0, and the cosine of the y value at 0 degrees is the x value, which is 1. At pi over 2, we're up here, and the sine is the y value, which is 1, and the cosine is the x value, which is 0. Then we're over at the angle pi, where the sine is 0 and the cosine is minus 1. And finally, we're at the angle 3 pi over 2, 270 degrees. The sine is minus 1 and the cosine is 0. So the sine is minus 1 and the cosine is 0. So that does it for the 18 problems on this assessment test involving algebra, mostly algebra, a little bit of trig at the end. I would expect that you knew how to do some of those already, maybe all of them already, I hope. But for those of those where you missed them on your assessment test, please go back to the, please make sure you look at the part of the video where we go over those problems, and that you are familiar with all those techniques that we used and could do a similar problem. If you have any questions on any of these problems and you want to meet me in the office hour to go over these techniques for any of these problems in more detail, please do so. But watch the video completely for all problems that you did not get fully correct on this assessment test, to be prepared for any of these algebraic techniques that will eventually show up on the test in Calculus 1 and Calculus 2.